Right now, trillions of photons are slamming into your retinas every single second. You experience this simply as looking around, but this passive, effortless act of seeing is a biological illusion. This chart maps the entire electromagnetic spectrum. The universe is flooded with radiation, scaling from massive radio waves the size of buildings down to tiny, ultra-dense gamma rays. Human vision is confined to a microscopic sliver of this spectrum, between 380 and 700 nanometers. Because our biology is tuned to such a vanishingly small fraction of reality, we are effectively blind to the overwhelming mechanics of the cosmos. This diagram shows white light hitting a surface. When sunlight hits an apple, the material absorbs most wavelengths, but physically rejects the long red ones, which bounce outward toward your eyes. The sky appears as a physical blue canopy, but the effect is caused by short, high-energy wavelengths colliding with atmospheric gases and scattering in every direction. The apple itself holds no color. The sky holds no blue. These wavelengths carry energy, but color exists only as a biological translation within the brain. To understand the actual mechanics of the universe, we have to strip away human senses and examine the quantum source code, the photon. This atomic model shows the origin point of light. When an energized electron drops to a lower energy state, the atom ejects the energy difference as a discrete packet. For centuries, physicists debated whether these packets were solid particles, as Isaac Newton proposed, or continuous waves rippling through a field, as mapped by James Clerk Maxwell. The photoelectric effect challenged both models. High-intensity light failed to move electrons unless the light reached a specific frequency. The energy was locked in the frequency of the beam, not its volume. In 1900, Max Planck proposed that energy does not flow in a continuous stream, but exists in discrete, indivisible packets called quanta. Albert Einstein used this concept to prove that light operates as individual packets of energy, which were later named photons. By 1923, Arthur Compton demonstrated that when light collides with an electron, it transfers momentum, behaving exactly like a solid object. Physicists, including Erwin Schrödinger, eventually concluded that every photon possesses the properties of both waves and particles simultaneously. This dual nature defines the photon as a paradoxical entity operating under a set of rules that do not align with human intuition. Niels Bohr formalized this with the complementarity principle. The wave and particle traits of a photon are mutually exclusive, and upon observation we can measure one or the other but never both at once. Observation itself presents a physical obstacle. To pinpoint a tiny electron, we must bounce a high-energy photon off it, but the force of that collision instantly alters the electron's speed and path. Werner Heisenberg provided the mathematical proof for this dilemma, known as the uncertainty principle, which shows that complete precision at the quantum level is impossible. Quantum mechanics imposes a strict limit on observation. The energy required to probe a system at this scale inevitably alters the state you are attempting to measure. This quantum activity scales up into the macro world, especially when light is refracting through transparent matter like glass. Classical physics suggested that light simply passes through the empty space between atoms in water or glass. At the quantum level, a photon is absorbed by an electron. That electron vibrates, changes its energy state, and instantly fires off a brand new, identical photon. The apparent decrease in speed through water is the cumulative result of these micro-delays during absorption and re-emission. The absolute speed of light never actually changes, it is simply forced to navigate an impossibly dense traffic jam of quantum interactions. On a universal scale, this interaction between electrons and photons governs nearly everything in existence. Heat transfer, chemical bonds, and the structural integrity of your own atoms rely on electrons continuously exchanging photons. These continuous interactions define the universe as an infinite, invisible quantum conversation, with the photon acting as its primary language. A photon born in the Sun crosses 150 million kilometers of empty vacuum in exactly 8 minutes, traveling at 300,000 kilometers per second. That journey ends the moment the photon hits a single rhodopsin molecule at the back of your eye. Upon impact, the photon's quantum wave function collapses, transferring its energy and forcing the molecule to physically change its shape. This mechanical shift triggers a chemical reaction, firing an electrical impulse down the optic nerve and into the brain. In this fleeting biological sequence, the brain translates the raw quantum activity of the cosmos into the coherent experience we call reality.